are going to look at heat transfer from a mathematical perspective. We know that if something loses heat, something is going to gain that heat. Therefore, we can mathematically use the Q equals mc delta T to actually calculate the amount of heat transfer that is transferred from one thing to another. The one with the negative Q is the substance that loses the heat. The one with the positive Q is the substance that gains the heat. When you combine two samples together, eventually they're going to reach what's called thermal equilibrium. That means that they're going to be the same temperature. That's what we were trying to do with the coffee cup calorimeter experiment. We put the hot metal into there. The metal transferred the heat to the cold water that surrounded it. And eventually, the block and the water should have been the same temperature after the block was finished transferring all of its heat. When we do this section, it is really important that you watch your signs because positive and negative can be on two different things when we do this next mathematical formula. The positive and negative can show up on the temperature. So if it talks about temperature increasing, it's going to be a positive value. If it talks about temperature decreasing, it's going to be a negative value. The questions are also going to talk about heat loss and heat gain, which means that Q can be a negative or a positive value. Those are the only two things that should be showing up as possible negative numbers. If you start getting a mass with a negative number, be suspicious because it's not change in mass. It's mass. That means that the scale for communicating that starts at 0. You might have to put in signs. If it tells you that it loses heat or that it decreases temperature by 20 degrees Celsius, you might have to remember to add that negative. We'll skip this for now. We'll come back to it. Okay. Let's say we have two different beakers of water. Same amount of water in each beaker. Different temperatures. If I were to add the water from these two beakers into a third beaker, what would their final temperature be? So if I poured beaker A, beaker B together, and mix the water together, what do you think the final temperature would be? Same amount of water. Yes. Why? So somewhere in between. So logically, you have an understanding of what we're kind of getting at here. The heat from the particles in beaker A is going to be transferred to the heat in the water particles of beaker B. And because these water molecules in A are slowing down, and these particles of water are going to speed up, logically, we should be somewhere in between 30 and 50 degrees when we mix them together. Because we have the same amount of water in each beaker, we can predict that it's going to be somewhere in between, halfway in between. What if I change it a little bit? What if I say something like this? Let's say I have a test tube of water, 50 degrees Celsius, and I have a beaker of water at 30 degrees Celsius. What do you think the temperature is going to be when I mix them together? Okay, so why not 40 this time? Exactly. So the amount of stuff matters. The less stuff you have, the less moving particles can transfer their energy onto something else. So when we mix them together, we're going to predict that the final temperature is going to be closer to 30 than it is to 50. It's harder to make a very accurate prediction because we're not told volume. Is this a big test tube or is this a little test tube? If we're using a tiny test tube, it might even not change the temperature of the beaker of water. So does this make sense so far? So you already have an understanding of the basic principle of heat transfer and what we're getting at with this fancy word, thermal equilibrium. Now we're going to get mathy. What is this story about? Lots of words, lots of numbers. Try a picture. So we have a 0.200 kilogram piece of iron. Why would we want to heat up iron, do something with it, and then cool it down? If you want to shape metal into something, you have to heat it up first so that you can maybe strike it with a hammer or you can start bending it. When you are finished doing what you want to it, then you have to cool it down again. Why? Well, if you are giving a homemade sword to a customer that's just come out of the fire.
A hot iron doesn't work well. It kind of bends. It's very brittle.
And it will dent. You can't sharpen it. It's not really all that safe for a customer to hold. Yeah, the flaming sword idea, right? Okay, so this is a medieval example. All right, they would have a bucket of water beside the forge in the blacksmith shop. And then when they heated up something, I don't know, maybe it's a sword. This is not working well when it's out of alignment. And so they would heat up the sword, they would bang it, they would shape it, and then they would put the object into the bucket of water, whatever it was, to cool down the piece of iron. What is the heat transfer process going on in the bucket of water?
The iron is, I guess the water is absorbing.
Yes. So the heat is going from the piece of iron to the water. So is the iron gaining or losing heat? It's losing heat. That means that iron is going to have a negative Q value, right? Because it's the loser. Water is going to be absorbing the heat. It could absorb so much heat that sometimes that water would start boiling and steaming when they would put the metal item into the bucket of water. All right, so the iron is transferring the heat to the water. We know that if one item loses heat, the other item is going to gain heat. I'm going to put I here, or actually maybe I'll put Fe here for iron. And then I'm going to put W here for water. I'm going to do that because I'm going to expand Q. And I want to make sure I understand what mass of one thing is and what the mass of another thing is. Do you remember what the formula for calculating Q is? Okay, so Q equals mc delta T. That means this is mc delta T and Q equals mc delta T mc delta T. Fe just indicates iron. The W indicates water. I'm doing that because I have two of everything. I want to keep them straight. It looks scary. It's okay. Breathe. You'll be okay. You'll be okay. All right. We need to find the information that goes into this equation. I'm going to make some room. Okay. I'm going to go through and find and place the information from here. We have a 0.200 kilogram piece of iron. At 340 decimal degrees Celsius. It is cooled by placing into water that is at 22 degrees Celsius. The mixture reaches a final temperature of 24. So 24 degrees Celsius, that's the final temperature of the mixture, minus 340 decimal degrees Celsius. Should get 316. Excellent. The negative matters. The other thing that I need about iron is C, specific heat capacity. When I look through the stem, I don't see the specific heat capacity of iron. Oh, yes. Awesome. Find your chart. If you've lost your chart, it's back there behind Kelton on the board. Do you know what chart I'm talking about? Yep. Halfway down, you want to find iron here. Read across all the way to the last column. C equals 0.449. Whoops. joules per gram degrees Celsius. If I look at the units of specific heat capacity, I should be able to identify that I'm going to have an issue with mass. Can you see what that issue is? This one's grams. This one is kilograms. You need to change one of them. Which one is going to be the easiest of the two? Far easier. So, times 1,000 grams divided by 1 kilogram is going to give us 2.00 times 10 exponent 3 grams. Phew! That's just the iron side. Take this information and substitute it into here. Mm-hmm. Yes. I'm ignoring my work. Yeah, you're right. Okay. We need information for water. Now that I've got my iron stuff down in the equation, I'm just going to erase it so that I have space to do water data. Sorry? Okay. All right. Let's find our water information. How much water? Are we going to end up calculating M, C, or delta T if it's asking us how much water? So we don't know what that's going to be. It does not tell us about the specific heat capacity of water. Ah, good, and you're on the correct side. You can look all you want on the front side. You're not going to find water because this is all the elements. Why did you decide on 4.19 rather than 2 or 2.02? Specifically, in a liquid state, it depends. So when you read through the question, just make sure that you know that you're dealing with a solid or a liquid or a gas with water, because the values are very, very different. 4.19 joules per gram degrees Celsius. We also need a temperature change. Is it going to be the same temperature change as the iron? No. The final temperature of the water is the same as the iron, because once the iron sits in the water for long enough, they're going to be at thermal equilibrium. However, the water itself starts at 22 degrees Celsius and then ends at 24 degrees Celsius. So final 24 degrees Celsius minus the initial 22 degrees Celsius gives us a temperature change of 2 degrees Celsius. Please take this information and put it into this. There are several ways that you can tackle solving this question. I really like making the calculator do the work for me. If you want, you can find the product of everything on the left, the product that you have here on the right, and then do some divisions. I'm going to show you how to do the whole thing at one time in your calculator. Is that okay? Or would you rather me do it in parts? One step. All right. I'm going to write exactly what to do in your calculator. If I want to solve for the mass of water, and I have these two things, I need to divide by these two numbers. What I do to one side, I have to do to the other side, right? .19 divided by 4.19 is 1.
Can't you cross out the Celsius on the water side? Because doesn't it, the 2 Celsius and the joules per gram Celsius, doesn't it cross out?
Yes, it will. So C will definitely cross out here. Absolutely. Once I do that, I'm going to be left with this. All right, you got your calculators with you? All right, I'm going to tell you exactly what to punch in. Start off with a negative sign. Open bracket. 2.00 EE or EXP 2 times 0.449 times negative 316 and bracket divided by open bracket 4.19 times 2 in bracket equals. No? What you got? Okay, actually I'm going to pause this so people don't have endless conversations with me with.
changed it from kilograms. Didn't you have the same thing?
Alright, without any numbers, this is what our units look like. Okay, so grams divided by grams, Celsius divided by Celsius, joules divided by joules, Celsius divided by Celsius. This is 1 over 1 over G, which is grams.
Couldn't you just cross those? This,
Yep.
this, that.
Ooh, okay. So I'll rewrite this so you can see what James is referring to here. Times joules over gram degrees Celsius times degrees Celsius over joules per gram degrees Celsius times gram degrees Celsius. So James is thinking in groups of units, and that is awesome. He's recognizing this is the same unit collection as this. That means that this divided by this is going to be equal to 1. Degrees Celsius divided by degrees Celsius. And then you're left with grams. Absolutely. If you can make the calculator do this, it saves you a lot of work. It does require that you put your numbers in the correct spot and you remember to put it in negative sign if you need it. For example, if you had mixed up the temperatures and 2 was up here and negative 316 was down there, you would get a very, very different number. Part of the success with these problems is assigning your data and make sure you've got the correct mass with the correct substance. In this example, we are combining 2 different amounts and temperatures of water. What do you think could be a realistic scenario behind this question? Likely filling the sink with water. You started to fill the sink with water, and the water is too hot. So you've quickly turned on the cold water tap, and you've added in some cold water to try to make it a little bit more comfortable for maybe you to wash dishes, or maybe wash your hands, or wash your face. Because we have 2 different things of water, I'm going to call one water 1, and the other one water 2. Now, in terms of which one is which, it doesn't really matter, as long as we're consistent. So I'm going to propose that since we start off with 0.50 kilograms of water, that this is going to be number 1. The second sample is going to be number 2. Specific heat capacity is not given in the stem of the problem. Exactly. We need to look it up. By the end of this unit, we will know that it's 4.19 joules per gram degree Celsius because we will use it so much. Can you see an issue that we're going to have with mass? It's the same issue that we ran into the problem with last unit, or sorry, last question. This was in grams, this was in kilograms. I've tried to make the ink thinner to write with on the smartboard and it won't let me do it. So I'm often going to run out of room with these problems. I'm going to need to do the same thing with this water mass on the right hand side because it's also in kilograms. Then we have temperature change. Remember that temperature change is always your final minus the initial. This started at 50.0 degrees Celsius. That is the initial temperature. The final temperature of the water, once they were mixed together, was 20.0 degrees Celsius, which means the temperature of the substance has dropped 30 degrees Celsius. Oh, sorry. No, I'm mixing them up. Okay. Go to the work. Okay. Temperature change, we don't know because it's final minus initial, and we don't know the final temperature of each one. What we do know is the initial temperature of each. The initial temperature of the 5.0 times 10 to the 2 grams of water is 50 degrees. The initial temperature of water sample number 2 is at 20.0 degrees Celsius. Which of these two samples of water is going to lose heat? Yes, so that's going to be negative Q. Water sample number 2 is going to be positive Q. So we have negative Q equals positive Q. We're going to expand Q for each side. To differentiate between the units, anything associated with negative Q, I'm going to put a 1 behind their symbol. Versus positive Q, I'm going to put a 2 behind anything in their formula. How do we calculate temperature change? Always final minus initial. In addition to expanding Q, we're going to expand delta T. Gentlemen, I'll lose you really quick on this. I'll lose you really, really quick on this. This is the hardest that this question is going to get. I took Q and I expanded it into its MC delta T formula. I took delta T and I expanded it into TF minus TI. Now what I am doing is I am taking MC and I am multiplying it by what is in the brackets. So M times C times TF is going to be MC TF. This is a minus, but because this is a negative times a negative is going to be a positive. M times C times T, initial number 1, right there. I'm going to do the same thing for the other side. The final temperature of the two samples of water is the same, correct? I'm going to rearrange my equation now so that I have both final temperature combinations on one side. What I mean by that, here, this one has TF. I want to bring it to the same side as this one here, which has TF. And I'm going to do that by subtracting M2C2 minus F2 from this side. What I do to one side, I must do to the other side. I am also going to move the initial so that it is on the same side as this one, which also uses initial temperature data. This is positive M1C1 Ti, so I need to subtract it. What I do to one side, I must do to the other side. So if I rewrite this, I'm going to get the following. So I have the mass of water sample 1 times the specific heat capacity of sample 1 times the temperature, the final temperature of number 1. Subtract. Okay, I just gotta stand back. I should have done it in between step. Okay, so this is not easy to do on a smart board in front of. So teachers make mistakes too. Okay, so I'll do this again and make sure I've got it right. So positive and a negative, that is going to cancel out. M2C2 TF2. Okay, I did have it correct. I lose track too. This is not easy to do in front of 20 people, even when you work it out the night before. I have doubts when I do math work. I'm not a confident math student, okay? It's okay. It is a lot to keep track of, and that's why I know I get confused sometimes. I should have done the cancellation before I did the rewrite. Mhm. Exactly. The reason why it looks like all negatives change is because when I write out stuff, I always look at what loses heat and then what gains heat. So if you want, yes, take all of this because the whole thing is negatives. The other way is when you do this, you can do the positive Q on the left-hand side and the negative Q on the right-hand side. Okay. We have
No.
different color.
I thought you guys were
No, it's not that. No, it's not that. It's not that.
We're almost ready to solve the question. Almost. I know. This term and this term are the same. The final temperature for water sample 1 and water sample 2 is going to be the same because once you mix them, it's going to come up to thermal equilibrium. Nothing changes on the right-hand side because the initial temperatures are the same. The last rearrangement is going to give us just TF. Now we actually have the formula to solve for final temperature. Yes.
So you did all that just for that?
Ladies and gentlemen, this is physics.
I like that. Okay, this is the formula.